we started talking about, we were talking about the axiomatic definition of probability, right? And when we were talking about the axiomatic definition of probability, so yesterday we had started bringing in, we started off talking about the classical theory, and from there we moved to talk about the classical theory. I mean, we start talking about the axiomatic theory, and we saw that the axiomatic theory had, to some extent generalize the class of events for which probability theory was previously designed. So previously probability theory would only be executed if, or would be it would be possible to develop the theory if and only if the events were mutually exclusive in nature. But with this particular framework, with the with the axiomatic framework coming in, we saw that we could also we could also calculate the probability for different other values, for different other kind of events apart from uh, your yes. So what we saw was that we could also develop the probability theory apart from uh, mutually exclusive events. So events which were not mutually exclusive could also be modeled using the probability theory. But again, the problem that remained over here was that even though this axiomatic theory was, to some extent, it was, generalizing the problems that the classical theory of probability had. Even though it was doing that to some extent, but it it was still limited to work, and but the application was still limited to events which were discrete in nature, events which were discrete in nature. So for random experiments where outcome became continuous, both axiomatic and the classical probability had failed. So therefore, to overcome this problem associated with the discrete outcomes, what came into problem, or what came into, what with the method which became very famous, was the theory of mathematical probability. So the idea now with mathematical probability was that instead of writing out a random experiments and outcomes in words or in text forms, right, or in or instead of describing them very specifically, what we'll do is we will try to generate them in a mathematical framework, right? So this is where the concept of mathematical probability came into being, and it really helped in solving the problems with the very specific discrete events. And it really became, very handy because people started framing models, or models now could be framed, which had where the, the variable was a continuous variable, and it had multiple outcomes and continuous outcome which was plottable on a real line. So that is what, and that is the point from where mathematical probability started coming in. And a very, very critical concept based on which this particular theorization actually stands is the assumption, or is the concept of a random variable. A random variable, right? So let us see what this concept of random variable is. What we have seen previously is that probability is used to model random outcomes, right? Outcomes where you know all the set of possible outcomes, but which particular outcome will occur in a given trial, that is what you do not know. So what our objective over here would be is to help them, or is to help model this kind of situations in a mathematical framework. So to start off, to introduce the concept of random variable, let's just consider this very simple example once again. So say I say that there is this sample space S, right? Sample space S, and within S you have two types of outcomes: heads and tails, right? Now when I talk about this sample space S, what happens over here? So I'm saying that okay, there are two possible outcomes: X, head and tail, and I know that these are the set of possible all possible outcomes, and out of this at least any one will actually occur. So now this is where when I talk about the experiment, I talk about it in a very textual manner. So instead of writing this, what I say is, let X be a variable which takes two values, 1 and 0, right? So X will take a value 1 if heads equal to 0, otherwise, right? So there is a probability of X equal, so the moment I write this sample space in this framework, right? So what you can see is that I'm just rewriting this sample space in a mathematical way. I'm just creating a dichotomous mathematical variable. The moment I create this variable, not only that this uh, the sample space gets represented in a mathematical fashion, but also what happens is that X equals to 1 and X equal to 0 comes in over here, right? So we can see that immediately not only a mathematical representation is done, but also uh, this entire sample space gets summarized as a variable, and this variable which summarizes all the possible outcomes of a random experiment is called a random variable, because I know that either 1 or 0 will occur, but which value will occur in a particular trial is not really known to me. So therefore this variable X becomes a random variable. Now when I create a mathematical representation of a random variable, when I create a mathematical representation of a random variable, the next thing that happens is the probability that I estimate, or the probability that I calculate, can be calculated as again as a mathematical function. So over here I can now say that given that this random variable is there are two possible probabilities. One is probability X equal to 1. The second is probability X equal to 0. So now what is probability X equal to 1? So obviously I can write it as a mathematical function, that probability X equal to 1 is equal to half, x equal to 0 is equal to half, right? So if I put these two things together, now if you think I can write it, I can condense it more in a mathematical fashion. So this becomes probability x is equal to x is equal to half if x is 1 or 0. If x equal to 1 or 0 is equal to 0 otherwise, right? So over here what I say is that the probability of x equal to x is half if x is 1 or 0 equal to 0 otherwise. So now if you have a look into this, you can see that I have brought out that entire random experiment which we were trying to describe in terms of our words or in a very textual manner into a mathematical framework, and I can actually generate the probabilities corresponding to the outcome via a mathematical function, right? So this is where you can see that I have, sorry. So over here what you can see is I can relate the mathematical function, right? Or I can generate the probabilities via a mathematical function. So that is, the probabilities can be generated be generated via a mathematical function. So therefore now this entire random experiment has had, now it has a more mathematical framework, and this framework is called the mathematical probability. Now what I'm talking about is a very basics of mathematical probability. The actual mathematical probability is much more complicated, right? But what I have over here is the very basics, or this is how the transition to the mathematical probability has happened, and it has happened with the concept of random variable, and this random variable has formalized or has helped in formalizing a random experiment into a mathematical framework. Clear? So there are two things that we need to understand till this point. Number one, what do I mean by mathematical probability? That is, what is the concept, or what is the advantage that mathematical probability has, or what is the generalization in probability theory that mathematical probability has brought about. And the second is what exactly is a random variable. So are these two ideas clear up to this point? Then I'll introduce the other concepts as well. Great. Now, after this, the next part that we would like to talk about over here is uh, we would like to bring in the other. So we'll now next introduce other concepts of this part. Now, what? So let's address this part, the generalization that mathematical probability brings about. Right now, let us think that this variable x that I have discussed over here, that I have written, this variable x, now it does not take any specific value. The sample space x is belongs to an interval, right? A comma b, right? So it talks about a continuous variable, x belongs to a comma b. So over here, x can take any values between a and b. So this, the outcome set over here is continuous. So now if I want to compute the probability of an outcome, how do I do it in this case? Okay. So over here, now let's, yes, as I was saying, so if I need to find out the probability of picking any one number between A and B, how will I do that? So basically, let's just draw this graph. So over here, it is A, and over here, it is B, right? Now, I want to find out the probability of getting a number C, which is lying between A and B, just the probability of getting C, right? I don't want to know what is the value in between or something. So what is the probability of getting C in this interval? Now what I'll do is, now if I were to talk about the classical definition, what would happen is I would have to count the number of events. But in this mathematical framework, I would not do that. What I'll say is that I'll create a function, say fx, right? I'll say that the probability of obtaining an x, so C can occur in how many ways? C can occur only in one possible way, right? And what is the total number of possible occurrences that can happen over here? So the total number of possible occurrences that can happen over here is nothing but this entire length, right? So it is b minus a, right? So 1 divided by the entire line segment is 1 by b minus a, right? So, and this will happen as long as b is greater than a, else it is equal to 0 otherwise. So if I specify b and a such that b becomes less than a, then that is not going to happen over here. B has to be greater than a in order to have a given probability, right? Clear? So over here you can see that I can generate the probability not only for discrete outcome in this mathematical framework, but also for continuous frameworks. Clear? And it is this part that the new framework contributes to. So what we can see from here is that, so okay, so basically up to this point, is it clear? Okay, so basically over here what we see is that, you know, okay, I think I missed out something. Okay, so Preeti, you had a question, probability x equal to x. Okay, so over here what I'm saying is, in this case probability x is the random variable. So when I say that probability x equal to x, what I mean is the probability that the random variable x takes a value small x. Okay, so basically what I can see over here is that the moment when I feed in a value of this random variable x, the function gives me back a probability value, right? So therefore this is a function, so corresponding to a given dependent value, independent variable, there is a value of a dependent variable which is generated. Now when I do this, right, the next part that I need to understand is, so what are these functions, right? So I have one I'm writing as probability x equal to x, the other I'm writing as fx. So what are these functions? So these functions, these functions are known by very specific names. So this particular function that I have for random variables with discrete outcomes, so functions which summarize the relationship between the discrete outcomes of a random experiment and the probability, is called the probability mass function. This is called a probability mass function. And the function which maps and the function which maps the probability to the continuous outcome of a random experiment, that is called a probability density function. This is called a probability density function, right? So let us define these functions in more details. Let's start off with probability mass function. So obviously one thing we have seen is that this mathematical, so a probability mass function is a mathematical function which maps the discrete outcomes of a random experiment, right? So it maps the discrete outcomes of a random experiment to its probabilities. So therefore, there are two things about this function. The first property that this function must satisfy is that no matter whatever value of probability it generates, that value has to be greater than equal to 0. So no matter whatever value you generate, right? So this probability x greater than, so x equal to x. So whatever probability value you generate corresponding to a given outcome, this is always greater than equal to 0 for all x. And the second part is, since each of these outcomes, since the function gives me probability values, therefore when I add up all the probabilities corresponding to all the outcomes of the random experiment, that summation should give me the value 1, right? Clear? So basically, since a probability mass function shows the, or it maps the probability to the outcomes, right? Therefore, each of the probability is greater than equal to 0, and the summation of all the probabilities is equal to 1, right? So let's see. Say let's take this coin tossing example that we have used over here. So how does the function go? It says that if x is 1 or 0, right? If x is 1 or 0, the probability will be half. Otherwise, if x takes any other value, so if it takes any other values, then what will happen is it will, if x takes another values, then the probability will be 0, right? So if I have a look into this, so let's see whether these two characteristic is satisfied for this function or not. So does the function, does the coin tossing example satisfy these two properties or not? So let's check the first property. If you check the first property, you will see that for probability x equal to 1, probability x equal to 0, the values for x equal to 1 or x equal to 0, the probability value or the function takes a positive value. It takes the value half, right? However, if it is not 0, say take any other value, like say take x equal to minus infinity, x equal to minus 1, like this, take up any value apart from 1 and 2, probability x equal to infinity is always 0. So that means either the probability x equal to 1 is, for probability x equal to 1 and probability x equal to 0, the probability is greater than 0. So if x, so x takes two values, 1 and 0. So there are just these two possible outcomes. The others are impossible in nature. So you cannot have an event or you cannot have an outcome where the probability is negative in value. So your probability should always come out as a positive, as a non-negative value. So either it should be greater than 0 or it should be equal to 0. There can be no negative values. Just a minute, guys. Hey, hi Anirudh. Sorry, I just someone was there at the door, so the boy was there at the door and he's like, sorry. Okay, so let's start. So over here, so what we can see over here is that in this probability or in this function, so either, so there are two possible outcomes. So it is only for those two outcomes that the probability is greater than 0. For outcomes which are impossible events, so which do not occur at all in the given random experiment, therefore it becomes so the probability is 0, right? So either the probability is greater than 0 or it is equal to 0. It can never be negative. And the second is, if I add up all the probabilities, so if I add up all the probabilities from minus infinity to plus infinity, right? So even if I work, so basically if I add it all up from minus into plus infinity, then we need to then we should always end up with 1, because if you add up all the possible probabilities you will always end up with 1. So basically if I arrange this part in that term, we can say that x equal to minus infinity to minus 1 probability x equal to x plus summation x equal to 0 to 1 probability x equal to x plus summation x equal to 2 to infinity x equal to x. So obviously we know that this part will have the non-zero value, because the outcome, there are just two outcomes, 1 and 0. So over here I'll have probability x equal to 1, I mean x equal to 0, plus probability x equal to 1. So then this is half plus half 1 plus, so this part is 0, because 2 to infinity, there is no, x does not take a value between 2 to infinity, x only takes value between 0 and 1, only 0 and 1. Therefore this part is 0. Also x does not take any negative values, minus into minus 1, this part is also 0. So if you add up all these values together, what you end up with is 1, right? So is this idea of the probability mass function clear? As to why a probability mass function should satisfy these two characteristics, is this part clear to us? Or are there any queries? Think about it for the next 2 minutes and then we'll take it up. I'm just going on mute. Once, so after 2 minutes, I'll just unmute and then we'll start. Hey, hi. Okay. So now let's move on to the next concept. So from probability mass function. So no confusions regarding probability mass function. Everything clear? Great. The next part that we have is the probability density function, right? So basically, when there is you know, there the outcomes are continuous in nature, like this in this case. Then what we define is not a probability mass function, but we then define a probability density function. So the only difference between a probability mass function and difference function is in the nature of its formulation. Given that one is defined for continuous variable and the other is defined for discrete variable, right? So over here, how would a probability density function look like? So obviously, when I talk about a probability density function, right? Uh, the function or the way the function or the framework will just be changing, but the overall the overview does not actually change. So over here what we have is we say that the function fx is greater than equal to 0 for all x. So no matter whatever the outcome is for all x, fx is greater than equal to 0. Now the next part is over here, if I sum up all the values of x from minus infinity to plus infinity, right, the probability of it must ultimately come up, must add up to 1. Fx dx is equal to, right? So therefore, when I look into this, so this is just another way of defining. Now, when I talk about these mass functions, when I talk about these probability mass functions, always remember that no mass function can be formulated without any assumption. So, be it a probability mass function or be it a probability density function, there are certain assumptions under which a particular mass function can be, you know, formulated. Now, when a particular, when this probability mass function or density function is framed under an assumption, then those assumptions are not just, anything just made out of something. So what happens is this assumption, or the assumption that we have are nothing but necessary conditions. So they are necessary conditions. There are some necessary conditions required for generating or required for an experiment. And say for example, when I'm tossing the coin, for this coin tossing example, right? So for this coin tossing example, what would happen is we would say that there are a set of certain assumptions, right? And for these assumptions, your so basically when I'm tossing the coin, so the question that comes out over here is that okay, so there are just two outcomes, there are discrete events, and also under these assumptions, under these conditions, the coin tossing experiment is executed, right? So therefore, what should happen or what happens is that with these assumptions in place, I can actually create a mathematical framework of this of a random experiment, and that is called a probability distribution, right? So with this mathematical framework, what I can do is I can create out schedule showing the outcomes and the probability of the outcomes, right? So that is where this concept of mass function and probability density function becomes very important, right? So they help us generating, or they help us in creating more generalized structure of these statistical experiments. So for example, say I have written over here that the probability x equal to x is equal to half if x is 1 or 0, right? Now this is a very specific value that I have provided. Now using this probability mass function, I can also generate, I can create a more generalized version of this framework or of this random experiment. So what would it be exactly? So what is it going to be like? So over here, so let's say that I'm saying that probability x equal to 1 is half. But you can see that this is a very specific constant value which is defined over there, right? So from here, what we want to do is we want to generalize this framework, right? So how do we go about generalizing the framework? So let's say I'll just take a backtracking part. I can say, guys, Preeti is unable to hear me. Are the others able to hear me? Prakash, Anirudh. Okay, okay. Thank you. Thanks a lot. I think Preeti is joining better. Okay, so over here, what I've said is that if probability x equal to 1, or the probability of x equal to 1 is half. Now I can actually create a more generalized expression out of it. Say I tell you something like this, that half is nothing but half into 1. So I'm not doing any derivation over here. I am just backtracking, and I'm just trying to show you that this value that I have over here is a very specific form of a more generalized expression, right? So half is something like half into 1. Now over here, 1 is nothing but something to the power of 0 is 1. So I can say that 1 is nothing but half to the power of 0, right? So therefore I can also say that this half to the power of 0 into half is nothing but half to the power of 1 into a half to the power of 1 minus 0. So therefore, if I think about it, I can say that probability of x, take the value x, can be represented as half to the power of x into half to the power of 1 minus x. right? So it shows that this is x equal to x is half to the power of x into 1 x if x is equal to 1. So you can see that this function, which has just simply started off by taking a simple value half, is gradually graduating into a more generalized functional form. Now similarly, I can say that if so, this is the relationship that would hold between x equal to 1 and the probability x equal to x. Similarly, the next part that I have over here is x equal to 0. So x equal to 0 is also half. Very carefully observe this backtrack exercise that I'm doing over here, right? Because I'm trying to bring out the fact over here that this probability mass function or the broad density function is a more generalized mathematical framework, and that mathematical framework has very important relevance to the next stages. So even though this might seem like a simple backtracking exercise, but I would suggest you to look into it very carefully. If you feel anything uncomfortable, if you feel that you're being unable to understand that, or there are any challenges in your understanding this, feel free to ask, clarify your doubts. Right. Say over here, I'll say half. This is half, right? So I'll say that this is now 1 into half. So this is half to the power of 0 into half to the power of 1 minus 0. Sorry, this would be 1 minus 1. Right, so therefore what I can clearly see is that this is nothing but half. So over here again, I can write it as half to the power of x into half to the power of 1 minus x. So generally, this function that you or this value that you get to see comes out or it stems from a more generalized version of the function of this mathematical form. And it is this mathematical form which is giving me the relationship, which is giving me this value, right? So this generalized mathematical form is called a probability distribution, right? And taking up all these factors together, all these factors together. So what we have over here is a probability x equal to x, which can be written as half to the power of x into half to the power of 1 minus x. If x is equal to 1 comma 0, otherwise it's equal to is equal to 0 otherwise. So now this is a very generalized mathematical framework of this functional values that we saw till now, and this is called a probability distribution, and it has a very specific name called the Bernoulli's distribution or the Bernoullian distribution. Right, so this is called the Bernoulli's distribution. And now if you think about it, for every values of x I can actually create a schedule. So basically I can say that there is x, so x is 0, the probability of x is half. To take this value is half. X is 1, the probability of x to take this value is half. So I can actually create out a schedule out of it, right? And then what I can also do it, I can plot this and this in a graph, and hence this is nothing but a distribution. So this is nothing but a distribution, right? And this is called a probability distribution. So I can think about a probability distribution as a mathematical function. So it is nothing but a probability mass function or a probability density function which has been created under certain assumptions, right? And one of the biggest assumption that this distribution has, or this mathematical framework has, is that there is only a single trial. There is a single trial, and this distribution is known as a Bernoullian distribution. Now, apart from having a single trial, there are other assumptions to this particular framework, right? So what is that assumption? The assumption, the second set of assumption that it has is that each outcomes are mutually exclusive. Outcome is mutually exclusive, right? And that each outcome has or each event has two possible outcomes. That is either a success or a failure. Right? So events which satisfies these characteristics are said to follow binomial distribution, a Bernoulli distribution, or said more generally, or said in a more general framework, each of these trials, each of these trials in a random experiment is also known as a Bernoullian trial, because each of the trials they satisfy this possible or this characteristic, that is one single trial which has one single trial which leads to an event which has two outcomes, either a success or a failure. So there can be nothing in between. So either you succeed or you fail. So when there are two outcomes and each of them has two respective properties or has two probabilities of occurring, then then that is called a Bernoullian trial. And this is precisely the reason as to why the lending process also is said to be a very good example of Bernoullian distribution. So there is a borrower who comes in, right? And there is a borrower who comes in asking for a credit. You give out the credit to the borrower. Right now, you do not know whether he is a good borrower or a bad borrower. So there are two chances. Number one, the borrower can be a good borrower and he may pay back. The second is he is a bad borrower and he may not pay back. So that is the reason why each lending trial, so each loan that you are extending out, each credit that you are extending out is a simple example of a Bernoullian trial. Clear? And this is the most fundamental probability distribution that we can think about. So clear up to this point, clear up to the Bernoullian distribution. Clear? Great. The next part that we'll talk about is, so this is the most fundamental kind of a discrete distribution one can think about. So a trial is a fundamental frame or it's a fundamental component of a random experiment. Now if trial is it's a fundamental character, it's a fundamental occurrence, right? Then Bernoulli distribution, this distribution that I'm talking about, is also a fundamental occurrence because it characterizes a trial. So a Bernoullian distribution is described for one given trial, right? So this is the reason why this Bernoullian distribution, Bernoulli's distribution, is considered to be one of the most fundamental and basic distribution. Great. Okay. Like Bernoullian distribution is the most fundamental characteristic, of a discrete random experiment, right? The rectangular distribution is the most fundamental type of distribution for a continuous random experiment. For a random experiment where the outcomes are continuous in nature, right? So that gives us an idea about. So this gives us a fundamental idea about how the behavior of the variables are, right? So what exactly are the variables and so on. So basically, uh, just to reframe, what I want to say is that the uniform the rectangular distribution will give us a very basic idea about how a continuous density function or a continuous probability function can be created, right? Okay, so let's just review this basic continuous distribution, which I'm calling the rectangular distribution. Yes, Anirudh. I'll just repeat this in short. So basically, like the Bernoulli distribution is a fundamental, it's the most fundamental discrete distribution. Similarly, rectangular distribution is the most fundamental form of a continuous distribution, right? And the most and the easiest, and this function that I have written over here represents the rectangular distribution, right? So what's the rectangular distribution? How does the rectangular distribution work? And what are the different variations of this rectangular distribution? That is what we need to understand. Uh, so the rectangular distribution is generally defined as, sorry, fx equals to 1 by b minus a. Guys, just hold on a second. Okay. Okay, so this function fx is equals to 1 by b minus a, where b is greater than a, equal to 0. So how does this function look like? We have already seen. But what is the most important advantage of this particular form of the function? Now this function is a very simple function which helps us find out probability of, you know, probabilities of x which is less than equal to a given value, right? So that is what we have, or this is what we can actually show. or we can actually easily calculate. Say for example, I want to find out that what is the probability of getting a number x which is less than equal to this value c. So then how do I do this? So obviously what I'll do is I compute, so the probability of this function will be fx is equal to c minus a divided by b minus a. Right, so this part divided by this particular. Now if a is 0 and b is equal to 1, then the rectangular function is called the rectangular distribution comes to be known as, or is known as, the uniform distribution. Right, so this is called the uniform distribution. And the funniest part is that the probability of getting x less than equal to c for the uniform distribution will be c itself, because over here you see it's c minus a divided by b minus a, right? If a is 0 and b is 1, then this reduces to c. And this is a very important result which is used for sampling. This is a really very important result which is used for sampling, for splitting data sets into, model development, validation, and whatever we call it. So this is what the overall idea is. So these are the two basic distribution functions that we can think about, right? So the Bernoullian distribution function, the Bernoullian distribution is used to characterize the trials of a random experiment, right? Which has discrete uh, trials. I mean, the trials are discrete outcomes. So for that, Bernoullian distribution is very useful. On the other hand, this basic framework of the continuous distribution, the rectangular distribution, generalized, specified to the uniform distribution, is a very important distribution because it helps in creating specified samples in the process of model development, right? So, for example, right, we want to, so whenever we are developing models, right, so model cannot be developed on the whole data set which is available with me. What I need to do is I need to develop the model on a subset of the data and then validate that on another subset, right? So suppose if I have a data set which contains 20,000 observations, then I cannot develop the model on all the 20,000 observations, because I, after developing, I also need to know whether the model is robust in nature or not, and that is where I would need to validate that, right? So in order to validate that, what we'll do is we'll work with this framework, right? So what we will do is we divide that available data into model development data and into model validation data, right? And once this is done, once the division is done, model development, model validation data is done, then the model is developed on the development data and validated on the validation data. But the question is, how would the model be validated? How would the data set be split into model development and model validation? In order to do that, what happens is random. Say suppose there are 20,000 observations, right? Now out of these 20,000 observations, I know that roughly 14k observations will go into the model development data and 6k observations will go into the model validation data. Now how do I do this split? So for doing this split, random numbers are generated from a uniform distribution. Now I know that the probability, so out of all the random numbers generated, the probability of getting a random number less than equal to 0.7 will be 0.7 itself. So I now using that cutoff, what I can do is I can split the data into two parts, into model development and into model validation. Clear? So this probability function, this probability distribution function, the uniform distribution or the rectangular distribution, plays a very important role in creating model development and validation samples. Right? So let's stop here for the day. Okay, we'll continue with this. We'll talk about six important functions in the next class. We'll talk about binomial distributions. We'll talk about Poisson distributions on the discrete side. On the continuous side, we'll talk about the normal distribution, and from there we'll move into talk about sampling distribution, sample and sampling distributions. Uh, okay, so to your question, Aniruddha, I do not have, I do not have any document as such. No, no, no. I have a document. I have a Word document created for non-probability. I'll share that document. Right. And to your question, Preeti, so Preeti is asking that is it something that happens in the back end, or do we need to create samples using probability? So Preeti, we need to create samples using probability. So we'll have to generate random numbers from the uniform distribution, then basis that we split it into two parts, and then we need to take that up. So that is something that we'll be doing hands-on when we start off with things on the SaaS platform. Right? And Aniruddha, yes, I'll share that document on probability that I have. I'll share that. Just give me some time today, okay? Because okay, so thank you guys for your time. Next week we have hope to have the full 2 hours of session, right? And we'll take it up from there. Thank you. Bye bye. And in case you have any questions, please write into me.